All right, so let's try another scalar surface integral example. In this case, we're just going to do the setup, and I want you to try it first. I want you to put it on pause. See if you can set up part A would be finding the surface area of S, which we know this is just a hemisphere, so we know we could do that just via geometry, but I want you just to practice how you would do surface area, and then B, try the mass. So go ahead and put it on pause. All right, so we need S as a level surface first. So this is the hemisphere, x squared, let's do the whole sphere first. X squared plus y squared plus z squared is 9. So the top hemisphere is just z is square root of 9 minus x squared minus y squared. So one thing we could do for finding our level surface is we could say, all right, well, let's let 0 equal square root of 9 minus x squared minus y squared minus z, and then we could let g of x, y, z be this function that's listed here on the right of this equation. And we can do that. That would actually work out fine. But remember what we're using g for. Ultimately, we're trying to find a vector that's normal to our surface at a given point, and we're going to use the gradient scaled. And we take that vector, we dot it with p so that we can figure out, as we project a tiny little surface here, what the corresponding new area down here becomes. If, let's say, we were projecting onto the xy plane. So I remind you what we use it for, because it would be easier algebraically it'd be easier instead to use the entire sphere. So let's say this is option 2. I can think of the entire sphere and then let G be this. And this is going to be still going to give me a vector that's normal. It'll be to the entire sphere at any point, and we'll just use it for the top sphere, and I'll show you where it comes into play that we just consider the hemisphere. So I'm going to do this for G, and then I'm going to project the surface. So it's important when you're choosing to project the surface that if your surface is going to fold over onto itself, so like let's imagine this top hemisphere. If we did project it onto, say, the XZ plane here, you can see that I basically would have this thing fold onto itself, and I'd have one side hit the other side. And that means I'm going to end up needing to do 2 different surface integrals, one that's considering this half and one that's considering the other half. And so it's much easier to instead project onto a plane where your surface won't fold onto itself. So I recommend, so that I don't have to do more than one surface integral, I'm going to project onto the xy plane and let P be k hat. And as a reminder, that's just the vector 0, 0, 1. Okay, so now let's rewrite ds, assuming this is what we're going to use to project. First I'm going to need gradient of g. So this is 2x, 2y, 2z, which means that my magnitude is the square root of 4x squared plus 4y squared plus 4z squared, which ends up being 2 over this. And then I'm going to take the magnitude, the dot product of the gradient with my vector k. And so that's just going to give me the k component of the gradient. And that, in this case, is just 2z. So this means that ds, when I want to rewrite it here, reminder, it's the magnitude of the gradient over the absolute value of this dot product. In this case, it's k hat. And that's going to give me 2 over square root of x squared plus y squared plus z squared over 2z dA. So the 2's are going to cancel, and I'm just going to be left with square root of x squared plus y squared plus z squared over z. Okay, now here's where things kind of diverge depending on if we wanted to find just the surface area or also the mass. So let's remind ourselves, if I want just the surface area, then I'm just doing the double integral over my surface S ds. Oh, and let's make the colors so you can see. As opposed to, if I want the mass, I'm going to be doing the double integral over the surface of the density ds. Okay, so let's just do density. Okay, now in either of these cases, I can't evaluate in this form. I have to change variables, which is what I've been working on up above. So let's see how the change variables plays out for the surface area. So now instead of integrating over the surface, I'm going to integrate over the shadow of the region I projected onto. And so that, in this case, is just going to be this circle down here in the xy plane. So this becomes my r. Okay. And that's the region I'm going to be integrating over. And my ds is getting replaced with the square root of x squared plus y squared plus z squared over z dA. Now I'm not done yet because this step is telling me rewrite the integrand in terms of just two variables. So right now I still can't do this double integral because I have x, y, and z in it. So I need to go back, and this is where I'm going to take into account that on the hemisphere up here, z is equal to the positive square root of 9 minus x squared minus y squared. I'm going to replace that inside this integrand. So I now have the square root of x squared plus y squared plus 9 minus x squared minus y squared, which is going to end up just giving me 3 in the numerator. In the denominator, I'm replacing it with z, which is the square root of 9 minus x squared minus y squared, and then dA. I don't have my bounds yet, I just have my integrand. But now everything in my integrand is just in terms of x and y. And just to back up, most people say, wait a minute, where'd you get this 3? How did this become 3? But remember, on the surface, which is where I want to restrict my integration, on the surface, x squared plus y squared plus z squared is equal to 9, which means the square root of it will be 3 on the surface. And that's where I'm integrating over. All right, and the mass integrand, we can do a similar idea. So let's rewrite that one. We had the density given up here as x squared over the quantity x squared plus y squared. And so we're going to change variables here. We're going to now integrate over my region R. And the integrand, luckily the way I gave us density was already in terms of x and y. So I can just replace that here with x squared over x squared plus y squared. And then ds is replaced just like we did over with the surface area with 3 over the square root of 9 minus x squared minus y squared dA. All right, so now we're ready to set up bounds. This is where we need to really picture the region we're integrating over. So as a reminder, we have projected now onto this circle, and the circle has radius, this is in the xy plane. Circle has radius 3 because my sphere had radius 3. This is my region R. And now the question is, I'm ready to set up my bounds, but before I do, before I say, oh, let's keep this in Cartesian, you should be saying, wait a minute, if you're integrating over a circular region like this, instead of setting this up in Cartesian, you should, wait for it, that's right, convert to polar. So let's now take this, pretend that you just had this integral and this was back last chapter when we were doing polar, and you're switching it to polar. Okay, so my bounds now become, well, let's look at the integrand too. The integrand is going to be 3, oops, let's do the color so you can see. 3 over square root of 9 minus r squared in polar. And then the dA piece in polar is going to become r dr d theta. And then we'll do our bounds. So r in this case starts at 0 and always ends at 3, and theta is just going around 0 to 2 pi. Okay, and now we're ready to integrate, and we can see we can use a u sub with this, and in fact we can even decouple because now I have bounds that are all constants. So let's do that, and we'll see how we get back to what we should have known just geometrically, since this is the surface area of a hemisphere of radius 9, or radius 3, excuse me. Surface area is 4 pi r squared, so we'd expect this to be 2 pi r squared, half of that. So we'd expect this to be 18 pi, and you can see if you just decouple, which is going to end up actually evaluating to this once you just do the algebra or do the integrals here. This will become 2 pi here. This integral in blue you're going to need to do a u sub with, but when you do it at the end of the day you're going to get 3. And so we get back to what we expected, this 18 pi. Expected that just knowing the formula to start. Okay, so let's now do this for mass. So go ahead, put it on pause if you haven't already. Convert the mass integral to polar and then integrate. Okay, and so this is what you'll get here. The difference is you do have this a little bit more of a complicated integral with theta. I just remind you, you can use this double angle formula to rewrite this, and then actually I just went through a little bit of the integration in my head here to get us down to pi for that green integral. So altogether we get 9 pi then for the total mass.